Hello, so we're going to be doing the FP2, the most recent one, as of April 2016, the most recent FP2 non-international paper. It was a paper that actually had quite high boundaries, so there are a few tricky bits, certainly not the first question, but even then they put a little bit thing in here, sticking a modular sign in to get 1 or 2 marks where you don't, we might have to think a bit. I'm going to use the squaring method that is quite popular for this type of question. I might look at the other possible approaches as well. So let's just look at squaring method, which is what's in the Heinemann textbook on this type of thing. Notice it's a strict inequality as well, so we don't have to worry about whether it's a strict inequality or not, because it's got to be a strict inequality here, because the original question, we'd have more to think about if it were like that. And we don't here. It's the first question. So we're going to multiply by x plus 3 squared. So we have x plus 2 times x plus 3 squared is greater than 12 times x plus 3. Right, now let's take that over to the other side, x plus 2 and x plus 3 squared minus 12 x plus 3 is greater than 0. Let's take x plus 3 out as a factor. So we have this, and let's multiply out. Plus 5x plus 6 minus 12. So we've got x plus 3 is greater than x squared plus 5x minus 6, which is greater than 0. And that itself factorizes. So that's x plus 6 and x minus 1 greater than 0. The beauty of this method is now we can just draw a standard cubic. It's going to go through minus 6, minus 3 and 1. And we want the times when it's above. So x has got to be between minus 6 and minus 3. And x has got to be greater than 1. So that's one way of doing it. I think I might look at more critical value kind of approach, which is a more general method, if you like, because I think it's better. It's good at this level to have more than one possibility. So we'll do that as well. So we'll talk about looking at critical values. So it's either or. We're not doing both of these. So if we rearrange this, we get x plus 2 is minus 12 over x plus 3 is greater than 0. X plus 2 times x plus 3 minus 12 over x plus 3 is greater than 0. And then multiplying out the top, I get x squared plus 5x. You might notice a similarity with the form of some of these. Over x plus 3 is greater than 0. So we have x plus 6, let's write it this way around, x minus 1 over x plus 3 is greater than 0. So we've got our critical values. Are 1 minus 3 and minus 6. Okay, so what we can say is, let's look at the regions that we could be looking at. If we've got x is less than minus 6, we've got the point x is greater than -6 but less than -3, and if x is greater than -3 but less than 1, and x is greater than 1, we can look at all of these three. Now, if x is less than -6, all of these three brackets are negative. Negative, negative over negative. So the whole thing is negative, so it's less than 0. Okay, so that isn't the part of the region that we want. If we've got x is between -6 and -3, then this one is certainly negative here. X plus 6 now becomes positive over negative, which is positive, which is greater than 0. If we have x greater than -3 but less than 1, then this one's still negative, but this is positive and this is positive. So that's negative, positive over positive. So then that makes the whole thing negative. So this is greater than 0. Sorry, less than 0. And then, of course, if x is greater than 1, then all three brackets are positive. So it's positive, it's greater than 0. So that means our final answer is this and this. Greater than 0 and greater than 0 applies for those two, which gives us our answer. Which gives us our answer. X is greater than, let's just change the colour again. That's what I was trying to do there. So that means that the final answer is x is greater than -6 but less than 3, and x is greater than 1. Okay, so that's our final answer for that question. Okay, now depending on which way you were taught this, or which way, if you're self-taught, depends on which resources you're using. You might say, oh, I prefer this way. I must say, for this particular question, I think the squaring method works nicely. However, it's not like that with maths. Sometimes another method might work easier for a different question. I actually think the second method here is a more general method, if you like, which might be more reliable in a greater number of cases than the squaring method. Although I think, having looked at most of FP2, the squaring method works very well in a lot of the cases as well. Okay, so that's question A done. Question B, well, question B is pretty straightforward, because if we look at our final answer here, instead of -3 there, if I look at our final answer there, if we're looking at this particular case, then x is negative, which must mean, and between minus, which must mean that this is negative, but this would be positive. So there's no way that the inequality can hold for this one. But it will hold when x is greater than 1, because the modulus will have no effect on it at that case. So the answer is just x is greater than 1. A 1 mark answer where it's where you're just expected to write it down. Before I go on to the next question, you might be wondering sometimes it says this, use algebra as though you would use something else. The thing is, people do have graphic calculators now, and so that's why they often say use algebra nowadays, because those who would actually use a graphical calculator, say, and plot y equals x plus 2 and y equals 12x plus 3, and then get the answers, will get no reward. As indeed would it be the case even if you did, and not, if you drew them, because they'd have no way of telling whether you actually use your graphical calculator or not. So which is why they say use algebra. It seems a bit strange, because probably best to use algebra anyway. Okay, so let's move on to the next question. Okay, so now on to question 2 of the FP2 paper, June 2015. Right, okay, so it says find the modulus and argument of this. I prefer to draw it in an Arzan diagram to just to make sure that we're okay here, minus 2 square root of 3, so we've got, it's minus 2 this way, so it's going to go to minus 2 here, and 2 the square root of 3 up here, so that's that point on the Argand diagram there. The axis out there. So it's that point there. So the modulus, well, the modulus is going to be equal to minus 2 squared plus 2 the square root of 3. The modulus squared will be equal to that, of course, squared. So that equals to 4 plus, that's going to be 4 times 3, 12. So that gives us mod z is equal to 16. Mod z is equal to 4. Okay. Now, the argument. Okay, so the argument will be equal to this angle here. So we need to take a little bit of care. Just simply putting arctan in the calculator and expecting us to get it right here is probably not to be advised. So let's just, what I'll do is I'll find this angle here and add it to 90. So this side here, let's do a different colour. That side there, because the x coordinate is 2, on this side here is 2 the square root of 3. So this angle alpha, tan alpha, is equal to 2 over 2 the square root of 3, which is 1 the square root of 3. So we have alpha is equal to pi over 6, but we're adding that to pi over 2. So that means going back to the question argument, we then have argument of z is equal to pi over 2 plus pi over 6, which is equal to 3 pi, 2 pi over 3. Okay, right, so notice if you just put it lazily, just say it's arctan minus 2 over 2 the square root of 3, then you're going to get, that's just laziness and you're going to get the wrong answer. It's going to, so you do need to take care when you find any argument when it's not an acute angle between 0 and 90. Okay, so that's, we now know, we're on to part B now. We now know that z is equal to 4 cos 2 pi over 3 plus I sine 2 pi over 3. Okay, so we want that to the power 6, so that's z to the power 6 is equal to 4 to the power 6 cos 2 pi by 3 to the power plus I sine 2 pi by 3 to the power 6. 4 to the power 6, 4096. Now we're using de Moivre's on here, times in this by 2, we get cos 4 pi plus I sine 4 pi. And without a calculator, we should see that cos 4 pi is equal to 1. Or is it equal to minus 1? In fact, yes, it would be equal to minus 1 because it's, no, it will be equal to 1, won't it? Yes, it will be equal to 1. So cos 4 pi is equal to 1. And sine 4 pi is equal to 0. So z to the power 6 is equal to 4096. Okay, now we're on to part C. Okay, part C, a bit of variation on a theme here, because we've got w to the 4 is equal to z cubed. So w equals to z cubed over 4. And we've got the z in modulus and argent form here. So we have w is equal to 4 to the 3/4. Okay, cos 2 pi by 3 plus I sine 2 pi by 3 to the 3/4. Right, okay, so we have 4 to the power 3/4. That's just going to be equal to the same as 2 to the 3 over 2. So that's 2 to the square root of 2. Okay, now we've got one possible answer here. So let's just work out a possible answer here by doing 3/4 here. I over 3 times 3/4. Okay, so that's w is equal to 2 to the square root of 2 cos pi over 2 plus I sine pi over 2. So one of the cos pi by 2 is equal to 0. So that would just be equal to 2 to the square root of 2. However, that's not going to be all the answers, because remember we've got a fourth root here. So probably if we go back to this line here and take multiples of 2 pi from, or even this line here, add on multiples of 2 pi from here and then divide by 3. So in fact w is equal to 2 to the square root of 2 cos right, so let's go to the original. 2 pi over 3 plus 2 pi n plus I sine 2 pi over 3 plus 2 pi n. Probably should have done this from the start, to be honest, but we've got the basic one here and we'll get the other 3 through what we're doing now, and we're still on 3/4 here. So we have w is equal to 2 to the square root of 2, and then that's cos, that's 6, 8 pi, no, let's write it out properly, pi over 3, and there's a 2 outside, 2 pi over 3, and then that's times by 1 plus 3n. Okay, and then something's not quite right here. Well, I've forgotten to do the 3/4, of course. That's very silly. Never mind. So we got, let's just do that before the 3/4. I think it was okay, in fact. 2 to the square root of 2 cos, and then we got pi times by, let's get this to pi over 3. I think this is just what I've just done, to be honest. 2, and then that's 1 plus 3n. I think it was okay. It's just I'd forgotten about the 3/4 here, and it didn't seem to be working. So that's I sine, also this is going to be the same, 2 pi over 3, 1 plus 3n. To 3/4. Now let's times by the 3/4 using De Moivre's. So that makes it cos, and the 3 cancels, and then that's pi over 2, 1 plus 3n, plus I sine pi over 2, 1 plus 3n. Okay. And when n is 0, we just get w is equal to 2 the square root of 2 as we had before. When n is 1, if we put 1 in there, we end up with w is equal to, this bit here will be equal to 4n, so that's cos 2 pi. So that would be equal to, there should be an I there as well, of course. That would be equal to w, still be equal to 0 here, but then I think this one will become minus 2 the square root of 2 over pi. Let's work it out. If we put n is there, 4n, that will be cos 2 pi, which would be equal to 1, so that would be 2 the square root of 2, and this one I think would then be equal to 0, because we'd have 4 there, divide by 2, sine 2 pi, that's 0. So if we put n is 2 in there, in this one in this one here we'll have 6n plus 7, so that's 7 pi over 2, which I think will be equal to 0 because it's an odd number, also divisible by 2, so that'll be equal to 0. But this one here, that'll be 7 pi over 2 as well, and that will be equal to negative 2 the square root of 2. And if we put n is 3 in, we'll get w is equal to, if we put n is 3 in there, we'll end up with 5 pi here. This one will be equal to 0, but then this one will be equal to the negative. Sorry about the phone going. So that's going to be equal to, when we put 2 the square root of 2 here, that's 2 the square root of 2i minus, because this one will be equal to 0, and this one, or the other way around. I think that will give us our 4 solutions. I may have these in a different order. I must confess I've done this without a calculator, but I'm pretty confident that the 4 solutions, when we put the respective values of 0, 1, 2 and 3, I'll rub them out just in case that's wrong. But if we put in consecutive values of 0, 1, 2 and 3, we're going to get those 4 solutions. I perhaps should have said that, but I was thinking aloud here. And not using a calculator, which is good practice, but perhaps a little bit more struggle than it should have been. Okay, on to the next question. Okay, so this is a differential equation using the integrating factor, question 3. Should be hopefully quite straightforward. We need to get it into exact form. So let's just divide by tan x on both sides. So we get dy by dx plus cot x y is equal to 3 cos 2x. So the integrating factor is e to the integral of cot x. Now, the integral of cot x is ln sin x, or ln mod sin x. The mod really doesn't matter here. So that's equal to sin x. So if I multiply these out, I get sine dy by dx plus, now sin x times cot x is just going to be equal to cos x is equal to 3 cos 2x sin x. Okay, now, so we've now got the left, when we've done that, the whole purpose of using the integrating factors, we've got it in exact form. So when we've got it in exact form, it'll be d by whatever's in front of this. If we've applied the integrating factor correctly, it'll be d by sin x times y by dx will be what it is above. And you will see if you use the product rule, it's good to check backwards, that if you use the product rule to expand that out, you would get what you get above, so it works. It should do if we've done the integrating factor right, but it's a useful check to see if it works. Okay, so now it's just a matter of integrating. So we've got y is equal to the, what sin x y is equal to the integral of 3 cos 2x sin x dx. Okay, so now in C4 this might have been a little bit of a stretch, but really in FP2 this shouldn't bother us. We could, there's two possible approaches really. We could just, I might be tempted to expand this out 3, and I'm going to expand it times 2 cos squared x minus 1 times sin x dx, which is equal to integral of 6 sin x cos squared x minus sin x dx. So that means that y sin x, would have been better to write it that way around. Let's change this now because it's clearer what we mean. So y sin x, now we're in a position to integrate this, I think. That is going to be related to cos cubed x, but it's not going to be exactly cos cubed x, is it? Because we're going to have, we need a 2, and we also need a minus in front of it for it all to work out. Okay, so we need a minus there, and integrating the minus sin x gives us plus cos x plus c. Don't forget the c. Okay, so then that gives us y equals minus 2 cos cubed x plus cos x plus c all over sin x. That's definitely my preferred way of doing it. It is possible also to use the product to sum formulae here, so I'll do that just for those. I think if it had been 3x here, then I think this is what I'd have gone for, but 2x and x I would normally expand and do that way rather than do what I'm going to do now. But I'm going to do it here just in case any of you have done this paper and thinking it might be wrong, because the answer looks quite different. Okay, so what we do is, because we've got combinations of coses and sines, we look at the formulae of sin A plus B, which is sin A cos B plus cos A sin B. And we have sin A minus B equals to sin A cos B minus cos A sin B. And then we need to have cos A sin B. So if we if we subtract these two together, if we subtract these two, we're going to end up with this. Okay, which means that we can if we sub in A for A is 2x and B is x, that means that 2 cos 2x sine x is equal to sine 3x minus sine x. So that means that we've got the integral of 3 cos 2x sine x coming back to here is in this 3 cos 2x sine x dx is equal to the same as 3 over 2 of sine 3x minus sine x dx. So that equals to 3 over 2 minus cos 3x over 3 plus cos x plus c. Tidying that up a bit, we'd get minus cos 3x over 2 plus 3 over 2 cos x plus c. So then we would, so that means that y sine x is equal to that. So that would give us y is equal to minus cos 3x plus 3 cos x plus c all over 2 sine x, which is exactly the same. I prefer what I did first. I prefer this in this case, but I'm sure that there will be plenty of people who've done this, because it might be that you might have seen something similar where you did it this way. It's quite natural sometimes to go for the method you did before, and it's fine. It does work. Yeah, just I think I'd prefer, in cases where we have 2x and x, other than 3x and x, or 3x and 2x, I think I'd prefer to expand in the way I did this one. So this is my alternative, if you like. Okay, so 6 marks, but we spent a bit of time looking at different methods for here. Right, now let's go on to question 4. Must admit I really like question 4, part B. It's something a little bit different. This theorem here, there may be a name for it, I don't know, but it's quite a famous, well-known one in number theory, that the sum of the cubes individually is the same as the sum of the numbers all together and then squared. It's quite a well-known theorem, and if you'd asked me to prove it, I wouldn't have been able to, but it has led you through, and we're not machines when it comes to doing mathematics, so sometimes we need a bit of help, and it has definitely done that for part B, but it's a bit different. So I know that last year it caused, it wasn't the most difficult paper, but this is one thing that did cause a few problems. Part A is a simple bit of algebra, so let's just do that. R squared, R plus 1 squared, minus R minus 1 squared, R squared, is equal to R squared, R plus 1 squared minus R minus 1 squared, which is the same as R squared times by R plus 1. I'm going to use a difference of 2 squares here, but we could just expand it out. Almost. That's going to be equal to, it's the difference of those two, so that's R plus 1 plus R minus 1 times by R plus 1 minus R plus 1. using the difference of two squares, or you could have just expanded them out, it doesn't really matter. And that gives us r squared times 2r times 2, which is 4r squared as required. 4r cubed, should I say? It should be r squared there. No, it shouldn't be r squared there, but we've got an r squared, so let's play with this. Okay, 4r cubed as required. Okay, so now on to this next part. Now, those of you, I'm not implying that this is step difficulty or anything alike, but those of you who are used to step and AA and that type of thing will have been quite used to feeling your way into a question. So you may not think, "Ooh, that looks a bit daunting. I've never seen anything like that." But it has told us to use the method of differences. There's only 4 marks. It can't be that much. It can't be that much to it. And this, we'll notice here, this left-hand side is at least the sum of the cubes. So let's just try and find what the sum of, we're trying to find a formula for the sum of the cubes and see if we can get anything from that. And we're going to use this formula for that. So in fact, let's go back to that. So let's look at 4r cubed, and let's look at different expressions for that. And let's play with this. So if r equals 1, we get 1 squared times by 2 squared. So we've got, this is all 4 sigma r cubed we're working at here. Minus 0 squared times 1 squared. And then we have, the next term is 2 squared times 3 squared minus 1 squared times 2 squared. It's not difficult to see what cancels here. 3 squared times 2 squared minus 2 squared times 3 squared. Dot, 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 dot. Right to the end. Here we have the last term we're putting in. It will be, when r is equal to n, we'll have n squared times n plus 1 squared minus n n squared times, so n minus 1 squared. So sometimes there's little background noises going on. So there we go, we've got that n minus 1 squared times n squared, and that is our method of differences. We're adding all these together, of course. So the sigma r cubed is equal to all of this. Now look at what cancels. We've got, obviously this is equal to 0 anyway. This cancels with this. This cancels with this. Let's do a double one to make it clear. That one cancels with that one, and so on. And so this one will cancel. So that's telling us, if we can go back to the blue here, 4r cubed equals to n bracket n plus 1 squared. Minus, going to put that in there just to show that we've used a method of differences. So that's telling us that 4r cubed is equal to n plus 1 squared. So if you've got this far, you've probably got you've got 2 of the marks anyway. But then it says so that it's equal to this, but it has given us a very, very helpful hint here. It's told us that sigma r is equal to that. Right, now that means, and there should be an n squared there, of course. Right, now, so that means that 4 sigma r cubed, let's write it like this, is equal to n squared n plus 1 squared over 4. So we have sigma r cubed is equal to n bracket n plus 1 over 2 squared. Do you notice anything here? It's given us this hint. It's equal to that. Now that's equal to sigma r. I probably ought to be putting in it's r equal to 1. Equals to which is what we've been asked to show. I might as well write out the line 1 cubed plus 2 cubed plus up to n cubed is equal to 1 plus 2 plus 3 plus 4 up to n squared as required. So it was almost having to work backwards once we got to this. Up to this point we've used the kind of standard method of differences, but then we needed to recognize that this was the square of this and then think backwards. So a nice question where we had to think backwards and work think outside the box a little bit, but not too bad. Okay, on to the next question. Oh, transformations in the complex plane. One of my favourite things. Okay, so transformations in the complex plane. It's going to be using modulus properties because you've got mod z equals 2, so it's going to involve rearranging this and getting on with it. So let's just do it. You've got w is equal to z over z plus 3i. So w bracket z plus 3i is equal to z. So wz plus 3wi equals to z. So wz minus z is equal to minus 3wi. So zw minus 1 is equal to minus 3wi. So z is equal to minus 3wi over w minus 1. Okay. So now we're going to use modulus property. We're going to use the fact that the modulus of z equals to 2. So we have mod of 3wi over w minus 1 is equal to 2. Okay, right, and that is going to be, okay, so 3wi, so that's going to be the mod of minus 3wi is equal to 2 the mod of w minus 1. This clearly is going to be a circle. Notice that any negative in a mod or any number can come outside, any negative can come outside, and any I can come. So in other words, using modulus properties, I'll write it out. Just really don't need to write this line, but I'm going to anyway. Mod of I is 1, mod of minus 3 is 3, so that's giving me 3 mod w is equal to 2 w minus 1, which is a circle, which is what they asked us to do. If you wonder why it's a circle, it's one of our standard ones, isn't it? Z minus Z1 is equal to K Z minus Z2 gives us a circle. But to find a centre and radius, we're going to be subbing in U and V anyway, so we can see it's a circle that way too. So let's sub in U plus IV. We have 3 then 3 squared, and then u squared plus v squared is equal to 2 squared. I'm probably skipping out a step here a little bit. Let's just go back a step. We've got 3, we're substituting w is equal to u plus iv. Okay, so we've got 3 mod u plus iv is equal to 2 u plus iv minus 1. So 3 u plus iv is equal to 2. Let's bring the real and imaginary parts together. It's good practice to do that. It's just generally what we should be doing. And notice the mod of z, the mod squared of any number, when we're eliminating a mod, we really got to get rid of i's and any negatives. It is simply, if we look at a number, and we call this mod z here, the length of it, and the z is equal to a plus bi, mod z squared using Pythagoras is a squared plus b squared. Okay, so when we're eliminating a mod, okay, so mod of a, the mod of a plus bi squared is going to be equal to a squared plus b squared. So there's no i's and no negatives when you're eliminating a mod. Okay, please, I see that so often where i's and negatives are all over the place. It's just the length in the R-SAM diagram. So that's going to be 3 squared, which is 9, u squared plus v squared is equal to 4, which is 2, but because it's 2 squared, u minus 1 squared plus v squared. Okay, so we have 9 u squared plus 9 v squared is equal to 4 u squared minus 2u plus 1 plus v squared. So bringing that all together, we're going to get 5u squared plus 5v squared, and then we've got minus 8u, so that's plus 8u plus minus 8, well, let's keep that on that side, equals to 8, I think. Yeah, minus 8u plus 8u. Okay, so now I'm going to divide by 5. So we've got u squared plus 4 plus v squared plus 8 over 5 u is equal to 8 over 5. So of course it's 4, isn't it? It should be 4 here. So completing the square for the u, I'm going to get u plus 4 over 5 squared minus 16 over 25 plus v squared is equal to 4 over 5. So I get u plus 4 over 5 squared plus v squared is equal to 16 over 25 plus 4 over 5. So that's equal to 36 over 25, at which point we're kind of relieved that we have a nice centre, 6 over 5, so that means it's a circle. Centre minus 4, 5, 0, radius, the square root of that number above, 6 over 5. Okay, so then we're nearly done. That's a simple 2-mark question. It says we've got mod z equals 2. Let's draw that. Our mod z, if we're in the z plane, we've got a circle here which is being mapped by means of this W is equal to Z over Z plus 3I. 2 points, and we've worked out the center and radius of this. It's going along 0 along the y-axis, but minus 4 over 5, so it's doing this, looking a little bit, it's kind of shrunk the radius a little bit, but anyway, it's doing that. And it's basically asking us where does this region map to? Now, if in doubt with this, I suspect it will be inside the circle as well. I have a strong feeling it might be inside the circle, but I'm not sure, to be fair. And often we have things where circles are mapped to one side of a line. So imagine if this circle was being mapped to a line somewhere and we had to decide which side of the line it is. My general policy is to pick the simplest point in the applicable region. So here, the most obvious one is Z is equal to 0. Well, where does Z equal to 0 map to? We'll put 0 into here, and we also get 0 there, because 0 over 0. So if that point which is inside also maps to this point which is also inside, then that must mean that the whole region is inside too. But had my test point come outside, then I'd be siding the outside of the circle and pick any simple point. The origin, it's a bit sad, isn't it? Pick any simple point that we can. The simplest being Z equals to 0 as your test point on the loci that you're considering, the region you're considering, and map it so it's inside the circle there. So then that's it, that's done. Okay, so that's the first 5 questions from the FP2 2015 paper done. We'll, in a separate video, I think, do the final, the next 3 questions. Okay.